Hey guys, this is Mr. Fourth Dimension. Welcome to the Geo project. So today we're going to keep working on line segment collision stuff. Last time we were testing this basic collision between a segment and a vertical segment, and we just got started. I don't remember how far we got into testing it, so we'll just start from wherever we left off. So that's going to mean we want to make sure that we test every case of a vertical line touching the line that's casting towards it and not touching the line, no matter which way we're casting the segment, whether it's, this way or this way or this way, or, away from the line as well. All of these cases, and also the cases, of course, where we actually collide with the line or overlap it, or however you want to think about it. So, last thing we had done, let's see. So these are the points for where to start, where to end, and we're moving this around, I think. So I'll just start with that. So first of all, here's a hit. If I put this in between, wait, that's the top, bottom. Okay, we're gonna move this X. So the X's are 3 and 8. I'm gonna put this right in the middle. I probably already tested this or something like it, but I don't remember exactly how far we got, so I'm just gonna start from the beginning of the testing. Okay. So that is a hit, and it's saying 0.4. Does that make sense? Between 3 and 8, there's 5 steps. So that would 5 steps means split up into step sizes of 0.2, and this is 2 of those. 5 is 2 away from 3. If this whole thing is 5 steps, then 5 is 2 steps in that direction. So 0.4 makes sense. Now we're going to take the X and push it all the way to 8. Yes, rebuild. Now it's getting a hit at 1. If I push this to 3, or, I don't know, not push, I don't know what I should call it, just move, slide, then I get a hit at 0. Now let's put it past the border a little bit. So that's a miss, and it's still calculating that, which is what we want it to do. We should check that that's correct. So if this is 5 steps, right, and each full integer is a step, then 9 is going to be 1.2, right? Cool. Now let's also try 2, which should be a negative 0.2, I think. Yeah. So those all seem to work, which is good. Now let's put this right in the middle. Let's mess with the y's. So actually I'm going to put this right on 7. I'll put this right on 8 to start, because the thing is we want to know where for sure we got to put this. So 10 and 4 definitely contains the range 5 to 8. But if I say I want to go from the top of 4 down to the bottom of 9, then that should no longer contain. Now the line should be, the vertical segment is too short and the cast is going underneath the line just a little bit. So that's a miss. Even though the T is at 1, the vertical line segment is not tall enough to actually contain. It's not in the right position and height to contain the rate cast. We can also move it below the 8, so that would mean going like 7 to 6. Good. Now let's try a slightly harder case where we put this at a 7 and figure out what we need to do. So at a spot of 7, we know for sure that something like 12, 10 shouldn't contain this, but let's say 8 and see if that shouldn't contain it either, right? But it's a little closer, so hopefully there's no bug there. Yep, that is a miss. And also, if we say it's definitely not going to be all the way down to 3, so let's use the range of like 4 to 3, so that should be a miss, I believe. Right, from 5 to 8, I believe that should be a miss. Yep, so that's 2. Now the segment's underneath the raycast a little bit. So I think that is pretty thorough. I think we've checked pretty much everything. The only other thing we could do is switch the order of these. Oops, that's not what I wanted. There we go. And let's put this back to something that we know will contain what we're aiming for here. So from 10 down to 4 always contains it. We'll put this at a 7. Now that's a hit. So the casting direction doesn't seem to matter. I think that was pretty thorough. So that concludes testing the first version of vertical collision. Let's do a quick round of testing this version. So we need to grab a full result. And that's going to go in place of this one. And this needs to be the full version, and that's all we have to change to make that work. Now the question isn't, is it a hit? Let's go up to Geo Cast Full. Okay, so it is a hit, but is it a hit of collision none, collision overlap, or collision tangent, right? So what we'll do is we'll say, instead of that if, we'll switch on the cast hit, and we've got a couple of cases: geo collision none, geo collision what are the other options here? Come on. Overlap, and tangent should be the last one, right? Cool. Then it'll look something like this on each of these. But this one should say miss. This should say overlap. This should say tangent. Alright, so let's see what we get here. So we get an overlap at 0.2, right? Yep, that makes sense. So if we put this at 8, we should get a tangent, I believe. Yes. Now what if we have this at 7? Well, let's test the other easy one, which is 3. Then we have to do a little math. 1. Perfect. Okay. And these are actually still in the reverse order. So we can just, if we want, we can redo it like so. There we go. It's a little messy, but we're good. And now what we want to try is, what if we put this on someplace in the middle? So we said it's 5 steps from 3 to 8. Let's make it 3 to 9, so it's 6 steps, and then 6 is right in the middle. Now from 5 to 8, it's 3 steps. So if it takes 6 steps to do this and 3 steps to do this, each of them is half a step. So if we're going to be 3 steps between these two, we're going to be 1.5 between these two. So that's going to be 6.5. Let's see if I put this at 6.5. And what makes this a tangent is that the vertical segment, right, if you think the vertical segment has 2 endpoints, one of the endpoints of the vertical segment should be right on the diagonal segment. So there's actually like 2 different tangent cases. There's the case where the ray has a point on the vertical segment, and a case where the vertical segment has a point on the ray. Now, of course, when we turn this into a general purpose, any 2 segments, there's no distinction between those 2 things anymore. But when the segment is a special line, its cases are special. But that is calculated as a tangent, so we're good. Okay, so that's a pretty thorough testing of the segment vertical collision function. Now the next big step, which we're not going to finish today, but we'll get started with the concept, is to make it use that to do this. This will be our first implementation of segment-segment collision, and maybe we'll find some other ways to do segment-segment collision, and we'll have to speed test them all. But for now, let's just say here's the one we're using, and then we can extend it with more later, if we come up with more options. So the basic idea is going to be, we can turn any problem into one of these problems by making a rotation of the space, by rotating the entire space around to a point where one of the two segments is vertical. So what we'll do is we'll say Q1 and Q2 need to become vertical. To do that, we need to take the angle between them. So it'll start with theta, which will be the original angle of Q1, Q2. And that we get we have a function for it, get geo direction, right? And geo direction, let's take a quick look at that function. It takes a single geopoint. So to make that happen, what we need to do, and this is where again it looks like maybe it's time we take a moment to do addition and subtraction operators, and maybe multiplication operator on these points, because I could just do Q2 minus Q1 here in that case. But we'll do this, so it's dq, so it's like delta q equals this, except it's make the point, which is q2.x minus q1.x, q2.y minus q1.y, right? So that makes the point, and then we just put that there. So maybe next time we'll take a break from what we're doing to get these operators cleaned up on all of our code, because that is starting to become a little bit of a hassle. And we'll just hope that it gets inlined and doesn't cost us much in terms of performance. Okay, so then we have this theta, and that was the direction from here to here. So now the question is, what do we do to rotate everything so that that becomes vertical? Well, what we really need to do is we need to figure out how much are we rotating by, because we're not rotating by this much. If this points straight up, that'll mean that it's pi over 4, right? So theta will be pi over 4 when that points straight up. And so we don't rotate by pi over 4 in that case, we rotate by 0. Now, if that is a 0, then we need to rotate by a positive pi over 4. And if theta, that is, if this thing is pointing to the right, if Q1, if the direction from Q1 to Q2 is pointing directly to the right, then that'll be a theta of 0, and we need to rotate it upwards by pi over 4. If, on the other hand, it's pointing to the left, so that it's an angle of pi over, if I've been saying pi over 4, it should be pi over 2. I always think that a quarter of a circle should be pi over 4, but it's wrong. So if this is pointing up, it should be pi over 2. If it's pointing to the right, it'll be 0, and we'll need to rotate it upwards by pi over 2. If it's pointing to the left, it'll be pi, and we'll need to rotate it backwards by pi over 2. So in general, the computation is that we take d theta, which is going to be the change in theta, and we say that it's going to be pi over 2, right? So we have, we have a pi constant in here somewhere, right? It's in math. Yes, pi. So we're going to take pi, and we're going to do pi over 2, and then that makes me think maybe we want these to be pre-computed constants as well. So let me put this here, and maybe we'll take a day from this project to do these constants. Actually, I'll just, for common square roots and parts of pi. So anyways, right now let's turn this into a times 0.5 pi. I prefer that. Alright, so that's the angle we want it to point to, and here's the angle it's coming from, so we subtract that. So if this happens to be equal to this, then it'll rotate by 0. If this is 0, it'll rotate by positive this much. You know, so this little d theta, this tells us how much we're going to need to rotate the entire space by. Now the last thing we need to do to get this start to the system wrapped up is we're going to want to actually do the rotations. So to do that, what we need are a sine of theta and a cosine of theta. And those we compute just like so, math sine d theta. And then we want the cos t. I don't think we have a math cosine yet, do we? So that's another good reason to have this open, at least. Cosine will be cosine, and these should be f's. There, 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 and there, and there. Alright, so that computes the sine of theta and the cosine. I'm going to write those out full. Cosine d theta, sine d theta, cosine d theta. Right, and then this is d theta, d theta. Okay, So next time we'll use these sines and cosines to rotate all of the points, and then we'll be able to start testing to see if we can detect any two collision points. But although I say we're going to do that next time, we'll probably have to do these constants and the operators next time. So we'll take a break from what we're currently doing, get this aside stuff done because it's starting to build up, and then we'll finally get back to this later. Okay, thanks for joining me. See you guys next time.